Hello everyone, thanks for being here. In this video, I will be talking about our group's recent work, a combinatorial approach to testing deep neural network based autonomous driving systems. This work is a collaboration with my advisor, Professor Dr. Lee from UTA, Dr. Kacker and Dr. Kun from the National Institute of Standards and Technology. As we all know, deep learning plays a significant role in the operation of autonomous driving systems. Deep neural network based models, or otherwise known as DNN models, are used to perform tasks such as obstacle detection, pedestrian detection, steering control, perception and localization, and route planning. As DNN models are trained and evaluated using a training dataset, uh, they could exhibit incorrect or unexpected behavior in real world scenarios. And there is a need to rigorously test DNN models, especially using tests that imitate real-world conditions and include corner case scenarios. Recent work from literature suggests that synthetic images generated using image transformation techniques can effectively identify the inconsistent behavior of DNN models. Zhang and al. proposed Deep Road, a framework that generates synthetic images that mimic two extreme weather conditions. Similarly, uh, another work from literature, Deep Test, demonstrated that testing DNN models with synthetic images generated with basic image transformation could produce inconsistent behavior. The findings from existing studies suggest that DNN models could exhibit several inconsistencies when executed with synthetic uh, images or test inputs generated using image transformation techniques. This forms the motivation for our study. We present a combinatorial testing based approach to generating synthetic images to test DNN models. The figure in this slide presents an overview of our approach. The goal of our approach is to generate synthetic images to test the pre-trained DNN models. In step 1, we identify basic image transformations that can be used to create synthetic test images. Then in step 2, we select our seed images. In step 3, for each seed image, we identify a set of valid transformation, that is, a subset of all possible transformations. We determine the validity by comparing the prediction results of the original image and the transformed image. A transformation is considered valid if the difference between the prediction results of the original image and the prediction results of the transformed image is less than a certain threshold, which is generally defined by the user. Then, based on the valid transformations, in step 4, we generate T-weight test set. To do that, for each seed image, we design an input parameter model where each transformation is identified as a parameter and the transformation values that make a transformation valid are identified as parameter values. In the final step, based on the input parameter model, we generate abstract T-weight test set. Then we derive the concrete test set, that is the synthetic images, by applying the T-weight image transformations to the seed images using the OpenCV framework. The synthetic images are used to test the DNN models. This approach is applicable for DNN that take an image as an input and outputs a prediction. We conducted an experimental evaluation of the proposed approach. Our experiments are designed to answer the following questions. 1. Can our combinatorial testing based approach successfully identify inconsistencies among DNN model implementations? 2. How does the combinatorial testing based approach impact the neuron coverage? A measure of number of neurons activated in a DNN model. I will discuss how we identify an inconsistent behavior in the later slides. We use open source DNN models from the Udacity Self-Driving Car Challenge. Among the top 5 ranking models from the challenge that are publicly available, we use 3 DNN models, namely Chauffeur, Rambo, and Autumn. as our subject models. As far as seed images, we select 19 seed images from the Udacity test dataset. Um, for image transformations, we use 7 image transformations, namely blur, brightness, contrast, rotation, scale, shear, and translation, with 10 values per transformations. Overall, we have 70 image transformations that are applicable per each seed image. However, each transformation uh, may not be uniformly applicable to all the seed images. Therefore, we identify a set of value transformations for each seed image. We measure our approach effectiveness by computing the number of inconsistent behaviors identified by a T-way test set. The more inconsistent behaviors the T-way test set detects, the more effective the T-way test set is considered to be. Given the nature of the domain, it is hard to determine an exact steering angle for the transformed images. Therefore, we identify inconsistent behavior under 2 cases. In case 1, we assume the T-way synthetic image and the original image shares the ground truth. Therefore, for each synthetic image, we measure the absolute difference between the steering angle of the original image and the steering angle of the transformed image. If this absolute difference exceeds a threshold, then we consider the T-way test to exhibit an inconsistent behavior. In the second case, we assume the synthetic image and the original image does not share the ground truth. So in this case, we compare the prediction results of the same synthetic image from the 3 DNNs that perform the same prediction. A T-way synthetic image exhibits an inconsistent behavior if it violates the equation shown in the slide. That is, if the maximum difference in prediction change across multiple models exceeds a threshold value. In addition to this, we use neuron coverage to measure the effectiveness of our approach. The notion of neuron coverage is defined as the ratio of unique neurons that is activated for a given input to the total number of neurons in a DNN. Next, we present the results and discussion about the results. First, for case 1, we used 3 thresholds, a threshold of 0.1, 0.2, and 0.3. Therefore, we're presenting 3 graphs in this slide. The x-axis presents the group number and the y-axis presents the percentage of T-way tests that exhibit consistent behavior. Recall that we generate T-way tests per group, and the total number of T-way tests varies among the groups. Therefore, we present our results as a percentage of T-way tests that exhibit a consistent behavior. Overall, if you look across the first graph, the one on the top left, that's for the threshold of 0.1. If you notice that, overall, Rambo model seems to exhibit a consistent performance for all the groups but group 10, where Autumn exhibits a better performance. As the threshold increases, Rambo continues to exhibit a better performance. In the next slide, I will summarize the results for case 1. To summarize the results for case 1, where the original seed image and the T-way synthetic image share the ground truth value, a test is considered to exhibit an inconsistent behavior if it violates the relation shown in this slide. So let's begin with threshold 0.1. For a threshold of 0.1, the Rambo model exhibits a very good consistent behavior, in a sense that for 8 groups, T-way test sets generated for Rambo model does not display any inconsistent behavior. Whereas for Schoffer and Autumn, more than 50% of T-way test cases in some cases resulted in an inconsistent behavior. An increase in threshold value results in a better performance, that is, a higher number of consistent behavior across 3 models. In the case of Rambo, with a threshold of 0.2, We observe that in most cases, all the T-weight tests generated exhibits a consistent behavior. Uh, However, for the rest of the two models, we observe that 25% of T-weight tests still results in an inconsistent behavior for some groups. For example, group 14, 17, 18, and 20 for autumn, and group 2, 8, 9, 12, and 16 and 18 for chauffeur uh, has a quite significant number of T-weight tests that results in an inconsistent behavior. We observe a similar pattern for threshold of 0.3. Overall, the results suggest that the Rambo model exhibits better performance compared to the other two models. Next, we present the results for case 2. In this case, the original and T-wave synthetic images might have a different ground truth value. The table presented in this slide uh, has 4 columns. The leftmost column and the first column presents the group number. Column 2, 3, and 4 presents the number of inconsistent behaviors detected for 3 different thresholds. And the last column presents the total number of test cases for each group. For a threshold of 0.1, you can observe a significant number of inconsistent behavior is being detected across all groups. As we increase the threshold, we see a decrease in number of inconsistent behaviors. Overall, the results suggest that T-weight test can detect a significant number of inconsistent behaviors across different thresholds. To summarize the results from case 2, with a threshold of 0.1, 18 out of 19 groups have at least 50% or more test results in an inconsistent behavior. In fact, for 12 groups, more than 90% of T-weight test results in an inconsistent behavior. And with an increase in the threshold value, we notice a decrease in number of inconsistent behaviors. And this is kind of expected. Next, we present the results of neuron coverage for the Rambo model. The Rambo model consists of 3 convolutional neural networks of models, referred here as S1, S2, and S3. The submodel S1 consists of 1625 neurons. Submodel S2 consists of 3801 neurons, and submodel S3 consists of 13,473 neurons. The graph presented in these slides, for all the 4 graphs, the x-axis represents the group number, and the y-axis represents the percentage of additional neurons covered by the T-weight test set compared to their respective baselines. Our results suggest that T-weight test set result in a significant increase in neuron coverage. Consider the case of S1. In S1, we notice a moderate increase in additional number of neurons covered, especially for 4 groups, group 10, 12, 13, and 17, we notice at least a 20% increase in additional neurons covered by the T-weight test set. For S2, we notice a substantial increase in neuron coverage. For 7 groups, groups 6, 7, 8, 9, 10, 11, and 13, we notice that more than 50% of additional neurons were covered by their respective T-weight test compared to their respective baseline. We observe that the T-weight test achieved a significant increase in neuron coverage for the submodel S3. Out of the 19 groups, T-weight tests generated for 11 groups achieved more than 100% increase in cumulative neuron coverage, among which 6 groups achieving more than 10 times increase in their respective cumulative neuron coverage, especially group 2, group 7, group 8, group 9, group 12, and group 13. We also notice that although there is a significant increase across all the groups in S3, you can notice that the cumulative neuron coverage increase for group 10 and 11 is very minimal. It's under 5%. This can be explained uh, as follows, which is that the seed images representing for group 10 and 11 covers uh, a, a significant number of neurons during the execution. In the case of group 10, the seed image covers 95%, almost 96% of neurons, and for group 11, the respective seed image covers around 94% of neurons. Therefore, T-weight test sets created for these two groups results in a marginal increase in neuron coverage. Overall, the results suggest that T-weight test increases the neuron coverage significantly. Uh, we also acknowledge that the neuron coverage results are unavailable for the remaining two models due to the time limitations, and we plan to uh, conduct this neuron coverage study for the other two models as a part of future work. To summarize, we presented a combinatorial testing based approach to systematically generate test images to test DNN models used in the autonomous driving systems. We performed an experimental evaluation of our approach with three publicly available pre-trained DNN models from the Udacity Self-Driving Challenge. We selected seed images from the Udacity test datasets, and we applied T-way image transformations on those seed images using our approach. The results suggest that the synthetic image generated by combining a set of image transformations successfully identify inconsistent behaviors. In case 1, overall Rambo model exhibits a better performance compared to the other two models. In case 2, for a threshold of 0.1, T-way images identifies a significant number of inconsistent behaviors across three models. Also, T-way test uh, significantly increases the neuron coverage for the Rambo model. As a part of future work, we plan to include additional weather-based transformations such as rain, fog, smog, and shadows, and generate T-way synthetic images to test DNN models used in autonomous driving systems. Thank you.